Welcome students. We want to discuss about fundamental theorem for line integrals. But before that, let's start with this beautiful quote by Archimedes. Mathematics reveals its secrets only to those who approach it with pure love for its own beauty. So this was a quote by Archimedes. We all know Archimedes, he's of Eureka fame. So let's start with fundamental theorem for line integrals. So recall, what was the fundamental theorem of calculus? So fundamental theorem of calculus was the following. So if you take a f prime, a continuous function on AB, then integral a to b f prime x dx is f of b minus f of a. So you take the antiderivative and evaluate it at the endpoint. So f of b minus f of a. Now we want to generalize this result to line integrals, right? So if you see any integral, it's first thing which makes sense to talk about is there a fundamental theorem associated with it? And the fundamental theorem for the line integral goes as follows. So let C be a smooth curve given by vector function r of t. So this is a parameterization for your curve, smooth curve C. Let f be a differentiable function of 2 or 3 variables. Let grad f be continuous on C. So instead of this f prime here, we are replacing this f prime with, in the case of line integral, we are replacing it by grad f, gradient of a function f. So grad f of f dot dr is f of rb minus f of ra. Note that your C is given by RT, where T goes from A to B. So in sense, RB is the final point. So the endpoints are RB and RA, right? So RA is the initial point of your curve C. So this is how your curve C is. The vector equation is given by R of t. This point is going to be given by R of A, and the position vector of this point is given by R of B, right? So you have this, that's f of RB minus f of RA. So your derivative here, in this case, is replaced by what? The gradient. So let's see the proof of this. So notice the following. We have C of grad of f dot dr is going to be integral. Now we'll put the parameterization in a to b grad of f of r of t. Now what is dr? dr is r prime t dt. But what is r prime t? So r prime t is going to be, if r is x, y, z, it has x, y, z coordinate, then it's going to be r prime is going to be dx by dt, dy by dt, and dz by dt. If you're considering the 3 variables, if you're considering 2 variables, then you're only interested in the first 2 components. So let me just write it down here. So we have r of t prime. So now when I replace this, this is going to be integral a to b. Now what is grad f? Grad f is partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of z with respect to, partial derivative of f with respect to z, dot with r prime is going to be dx by dt, dy by dt, and dz by dt times dt. Now if we look at the dot product, is going to be times dx by dt plus partial derivative of f with respect to y times dy by dt plus partial derivative of f with respect to z of dz by dt times dt. Now, if you look at this function here, this is a derivative of what? So your f is function of x, y, and z. And this in turn is a function of t. This is also function of t. This is also function of t. So essentially what you're writing here is, this is integral a to b d by dt of f of r t dt. Now we can basically apply the fundamental theorem of calculus from here. So if we apply this fundamental theorem, we'll get this is same as f of rb minus f of ra. So we get, if we have to compute this line integral, we get to this. Now let's try to appreciate this fundamental theorem. So first of all, if your vector field was f and it is equal to grad of f for some f, then you did not really care about the parameterization of r of t, right? In fact, it's not about parameterization. For parameterization, no matter what parameterization you take, the line integral remains the same. But for conservative vector fields here, you see that it depends only on the endpoint, r of b and r of a. So this only works for f, which is a form of grad f. That means it's what? F is conservative. So if it's conservative, things are nicer. So let's work on the following problem. So find the work done by the gravitational field F in moving the particle m from point 1, 0, 0 to 1, 2, 3. So recall, we have already done this problem the last time. So our F was same as grad of F, where F was given by mg upon length of vector x, which can be written as mg upon x squared plus y squared plus z squared. So in that case, we have what is the work done. So we are looking for work done by the gravitational field. So here we have W equals to integral over curve C, line integral over curve C, f dot dr. But in this case, we know that f is a potential function for grad. So this is same as grad of f dot dr. This is going to be, from the previous result, f of rb, which is same as f of rb. So we are taking r. So as you can see, it doesn't depend on what curve is joining 1, 0, 0 to 1, 2, 3, because it's only dependent on the endpoint, right? So you can, in particular, write this is going to be f of 2, 0, 0, sorry, 1, 0, 0. So we are starting from the point this to point this, right? So final point is 1, 2, 3. So this is going to be f of 1, 2, 3 minus the initial f of 1, 0, 0. So this is going to be mg upon square root of 1 square plus 2 square plus 3 square minus mg over square root of 1, which is 1. So this is what your work done is, all right? So this hints towards that no matter what path you took joining, so you took C1 or you took C2 or you took C3, your line integral here did not depend on the path. So then the question is, does line integral depends on path? And we have seen that already in the previous class that yes, the line integral depends on path for certain line integrals. And we now see here that in this case, if you have grad f as your vector field, then it does not depend on the path. So we should investigate this further. So let's towards that we need to build up some setup. So terminologies for certain terminologies for curves and regions. So a curve C is simple if it doesn't intersect itself. So a curve, this is say curve C is simple if it doesn't intersect itself except at the endpoint. Okay. So another simple curve is this is a simple curve. Now not simple is so simple. A non-simple curve would be non-simple curve would be say take a curve like that. Yeah, it intersects itself. Yeah, it need not be closed. Say for example, this is not simple, right? And simple are these examples here. Now a curve C is closed if it is initial point is equal to the terminal point. So for example, here, this curve is closed. This curve is also closed, but not simple. A region D is open if for every point P, there is a disk with a center that lies entirely in P. So you have a region. So basically, if you take any point P, if you draw a disk, it should lie inside. Yeah, with the center. But however, for this guy is not simple because if you take, so sorry, this region is not open, right? D, not open. Why? Because if you take a point P which lies on the boundary, you can draw a disk around it. No matter how small the disk is, it will still not completely, entirely lie inside D. So example of open region would be an open disk. You take a point here, you can't take a point on the boundary. So you have to take a point and you can always draw a small disk around it such that it completely lies inside D. Yeah. So a region D is connected if any two points can be connected by a path which lies completely in D. So here are the examples. So this is connected, right? Take any two points, you can join them. If your region D consists of these two parts, not connected, right? Not connected. Why? Because we can draw, if we join them, there is a path that if you take any path, that will not lie inside the D because D consists of only these two objects here. Okay, so here again, so simple but not closed, not simple, not closed because of the intersection, simple closed, not simple but closed. Why? Closed because it joins, the endpoint joins with the initial point and then, okay. So now we talk about simply connected region. So if D is simply connected region, if every simply closed curve in D encloses points only in D. So what do I mean by that? Take any curve like that. If you take any curve, closed curve, simple closed curve, and you join it, it will consist of only points which lie inside D. Say for example here, if you take any closed curve here, so if you took particularly this closed curve, then you can see it's not simple because there are points inside which do not lie in D. Of course, if you chose one here, you could say that this is a closed curve which entirely lies inside D, but that doesn't prove that it's simple, right? So simply connected region is no matter what closed curve you take in that region D, it should enclose only the points which lie inside D. So same scenario here too, right? If you took this one, this closed curve, it contains the points which are not in D. So this is not simple, right? Okay, so not simply connected, my bad. So this is the distinction between simply connected and non-simply connected, all right? So now, again, we want to understand the conservative nature of vector field. Again, reason is because line integral seems to be easy to compute when we are looking at the conservative fields. Reason again because they depend on only the endpoints. So we have the following theorem. So these results are equivalent. So let F be a vector field over a simply connected region D. Then the following are equivalent. F is conservative. That means that is there exists F such that grad of F equals to F. Two, that if you take any point x0 to x1 and you want to find out line integral of F, x1 of F dot dr, it does not depends on which path you take. So this integral will be, if you went along C1 or if you went along C2, you will get the same answer, same value. Third is the following, that integral over a closed path for all closed paths C in D will be what? 0. Note that our D is simply connected here, right? Region. So if you take any, so this is your region D, then if you take any closed curve, then the integral of closed integral F dot dr is going to be 0. Yeah. So this sign here is for this sign for the integral is for the closed curve. Okay. So these three statements are equivalent. All right. So let's see how we go about it. So definition. Let vector F be a continuous vector field with domain D. Then we say that this line integral is independent of path. If what happens if you take any two paths C1 F dot dr along C1 equals to F dot dr along C2. So this means that these two line integrals are same for any two paths C and D, C1 and C2 in D. So let this be C1 and let this be C2. Then these two integrals line integrals will have same value. So again, they depend on the initial point and the end point. So this is what we mean by a line integral being continuous, independent of the path. Okay. So note that we'll develop some equivalence now. So integral C F dot dr is independent of path if what happens if integral along any closed curve F dot dr is 0 for every closed path C in D. So suppose you are given that F dot dr is independent of the path. So we'll prove from here that this implies that integral over closed curve C F dot er is 0 for every closed path C in D. So so we want to show that this is going to be, now, so assume, so we'll say let C F dot dr be independent of the path in D. Now to show, so we are going this way, right? So to show that integral of f dot dr is 0 for any closed path C, for any closed path C in D. So let's start with the closed path. So let C be a closed path. So we have C, which is a closed path. So take 2 points A and B. So R of A and R of B. Yeah, these are the position vectors for these points. So let's call this as C1 and let's call this as C2. So what do we get? We get, because it does not depend on the path, what is a path joining? So this will be, if I put a minus sign here, if I change the path, I get minus C1 because I want to join RA to RB. So what does it tells me? The first part tells me that integral of C1 f dot dr with the minus sign is equal to integral of C2 f dot dr, right? Why is that? Since what? Since they join same points with RA as initial and RB as terminal points. I should be slightly careful when I say that because we are saying that these are the position vector of those points, okay? So this means when you bring it all on one side, so however, we can say this is same as saying minus of C1 f dot dr equals to C2 f dot dr. Now, if we add them together, we get C1 f dot dr plus C2 f dot dr equals to 0. So this means C1 union C2 because, well, C1 where C2, so C1 ends here and this is where C2 starts. So C1 union C2 f dot dr is equal to 0. But what is this equal to? This is equal to your curve C, closed integral over curve C, f dot dr equals to 0. So you have proved the following, that if you have f dot dr is independent of path, then the closed integral along curve C, f dot dr is 0 for every closed path C in D. Yeah, okay. So note, did we use conservative field here? No, we did not, right? So, but again, I mean, like it may depend on when is f dot dr independent of path, then we'll have to see the conservative. Okay, let's look at, so what about other way around? Other way around is to prove that if f dot dr is 0 for every closed path in C, then to show that it's independent of path, follow same process backwards. All right. Now let's look at the following. So suppose F is a vector field that is continuous on open connected region D. Okay. So you have an open connected region, open and connected region D. You have a vector field F acting on it. Then if F dot dr is independent of path D, then F is a conservative field on D. That means there exists F such that grad F equals to F. So we'll see the proof of this in the class, but notice the following, that you have integral F dot dr is independent of path, then we get what? F is conservative vector field. So this is telling you independence of path implies okay. So then the question is, how do we decide if the vector field is conservative? Now, why again? So let me rebuild the story. Let me retell the story. Why are we doing that again? Because we said if you take a conservative vector field here, right? If your F is grad F, if your vector field is conservative, then it doesn't depend on the path. Yeah. Now we are asking the other way around. If the integral is independent of path, is the vector field conservative? And the answer is yes. If F is continuous on an open connected region D, then F dot dr is independent of path. If it is independent of path, then it's conservative. So independence of path implies conservative on special domain, which is what? Open connected domain D. All right. Okay, so now the next question is, how do we decide if a vector field is conservative? So if I give you this vector field, how do we decide that it's conservative, right? So let's take a vector field F, where vector field F is given by the component of the first component is P of xy and second component be Q of xy, where P and Q have continuous first order partial derivative. But the theorem says if F is conservative, then dou P by dou y equals to dou Q by dou x. Well, why is that? Let's see. So we have vector field F is conservative. We get what this is going to be. This is PQ, and that is equal to grad F, which is dou F by dou x, dou F by dou y, right? Since F is conservative, we have, or there exists F such that vector field F equals to grad F. I'm not saying where the function F is from, right? It's a scalar function from R3 to, so, well, let's, in this case, since we have function of two variables, there exists F. So F is what? F is a function from D to R, okay? So now, if you look at dou P by dou X, or dou P by dou Y, my bad, you get what? You get partial derivative of, with respect to Y, and you get dou Q by dou X equals to dou square F by dou X dou Y. And these two are equal. Why are they equal? Because of two are equal because of Clairaut's theorem. Clairaut's theorem. Clairaut's theorem tells us that basically So Clairaut's theorem tells us that if you have a function f with continuous first order partial derivatives or first order partial derivatives, then the continuous second order partial derivatives actually, then the mixed partial derivatives are equal. So therefore we get that if f is conservative, we get dou p by dou y equals to dou q by dou x. So now this is an easy check. All right, this is an easy check to see if your vector field f is conservative. All right, now let's look at the following. So let D be a simply connected and open region in D throughout the D. And then we also have dou p by dou y equals to dou q by dou x. Then f is conservative. So we now have a way to check if a given vector field is conservative. So you just take f, which is p q, and it has to be defined on D, which is simple, connected and open. And all you need to check is dou p by dou y equals to dou q by dou x. And if it is, then your vector field is conservative. So let's see some problems now. First problem, determine if this vector field is conservative. And if it is conservative, find the potential function f such that f equals to grad f. All right, so first of all, let's look at this. This is your P and this part is your Q. Now we need to look at dou P by dou X, and we need to look at dou P by dou Y, and we need to look at dou Q by dou X. So these partial derivatives and see if they are equal. So let's see. So we have 2. So what is derivative of this with respect to y is going to be 2x sine y with a minus sign. Then we have minus cos x. What about dou q by dou x? So it's going to be x squared derivative is 2 minus 2x sine y, and derivative of sine is cosine x. So therefore we get y equals to dou q by dou x. Then the question is this enough to see? And the answer is no, you have to basically see what is a region D. So what is a region D? So region D, so what is the domain? Domain of F is, now this is defined for all of x, y. So all these terms are defined for all of x, y. So domain of F is R2, which is open and simply connected. Yeah, so here in the theorem, when I wrote this theorem, we mean domain D is open and simply connected. And when we have dou P by dou Y equals to dou Q by dou X, then F is conservative. So the simply connected part is important. Okay. So we have the following: dou P by dou Y equals to dou Q by dou X plus region is simply connected and open implies conservative. Note that this is important. This part is important here. This is an important aspect of it. We'll work on the following examples soon to see. Consider f of xy equals to 1 by x squared plus y squared times vector y, minus yx satisfies dou p by dou y equals to dou q by dou x, but is not conservative, We'll see that in a minute, okay? So however, let's finish this problem here. So we have f is, therefore we get f is y is conservative. Now part 2 of this problem is, so let's borrow part 2. Part 1, part 2 is find f. So we have, this implies dou f by dou x equals to 2x cos y minus y cos x. So if we integrate this with respect to x, we get integration of this 2x cos y minus y cos x dx, and integration is going to be x squared cos y minus, so plus y. So integration of cos is sine, so we get minus y sine x. Now since you are integrating with respect to x, there is a constant, and that constant could be function of y, right? Because if you take the antiderivative of with respect to x, there could be y, because derivative of y, function purely in y, derivative is 0. So now this is your f of x, y. Now take differentiate star. Star with respect to y and compare with dou f by dou y coming from the, so this is your dou f by dou y, right? So this part here is your dou f by dou y. So if you differentiate star with respect to y, we get dou f by dou y equals to, I'm going to differentiate this again, so I get minus 2x sine y, sorry, with respect to y, so x will remain as it is, right? The x squared will remain x, so cos y derivative is minus sine, so we get minus x squared sine y minus sine x plus hy of y, derivative of x with respect to y. This implies hy of y equals to 0. So derivative of h of y with respect to y is 0. So this means what? This means hy equals to c, some constant, and this implies your f of xy is equal to x squared cos y minus y sine x plus some constant c. Okay. You will see the similarity with exact differential equation if you are doing a course on differential equation, or if you will do the course on differential equation. Okay, so here now we were able to prove that it's conservative because of the condition being satisfied, and we were able to find the potential function f. Okay, let's do the following. So compute the integral of f dot dr where f is y squared by x squared minus y by 2x, the curve joining 1, 1 and 4, 2. So we're joining 1, 1 to 4 minus 2. And let's see, what is this integral? I'm going to draw this region slightly more properly. So first of all, okay, so we have 1, 1. So 1, 1. P is here, say 1, 1 to 4 minus 2. So 4, 1, 2, 3, 4. 4 minus 2. So 4 minus 2. And 1, 1 is not there. 1, 1 is on top here. 1, 1. And we have a curve C. We are not given information about curve C here. That's all right. So we will be able to compute this if your vector f, this vector field f was conservative, because in that case, it will not depend on the path. So we need to check if f is conservative. So first thing to check would be, write this as, so write your vector f as p comma q. And we have p equals to, so let's compute dou p by dou y. So this is going to be y squared by x squared, comma, minus 2y by x. So dou p by dou y is going to be 2y over x squared. Dou p by dou q by dou x is equal to derivative of this with respect to x. So 2y will come out. Derivative of 1 over x is minus 1 over x squared. So we get this guy. So therefore we have dou p by dou y equals to dou q by dou x. So seems like this is conservative, but hold on, we need to consider our region D. So what is D? So if we consider D to be this part of D, so consider D to be, we can restrict our domain and see if this domain is simply connected. And the answer is, consider D to be all xy such that x is greater than 0. And you see, it is continuous with the first order partial derivatives, right? So D is, in this case, is what? D is simply connected. Why is it simply connected? Because if you take any loop, all the points here, any simple closed curve, all the points are inside your region D. So this is your D. Simply connected open. Why open? Because this boundary is not there. So this is not there, right? So D is simply connected and open. That means what? F is conservative. Implies what? Implies the integral is independent of path. So integral is independent of path. So what is the integral going to be? C f dot dr is going to be grad of, so we need to compute the grad first, right? So this is going to be f of r of 4 minus 2, which will be essentially f of 4 minus 2 because we can take the unit parameterization. So f of 4, 2 minus, so initial 4 minus 2 minus f of 1, 1. Now let's compute. We need to compute f then. How would we compute f? So what is f? So f, that is, so it's conservative. That means there exists f from D to R. Again, conservative on D, not throughout the whole domain. So conservative on D, there exists f from D to R such that grad f equals to your function f. So we need to find out this f. Again, we'll have to use the antiderivative setup. So let's see. So we have f equals to, we need to find out f. If you compare, you will see dou f by dou x is equal to the first component, which is y by x, y squared by x squared. This implies dou integral of dou f by dou x with respect to dx. This is going to be my f of x. So this implies f of xy equal to this integral. Let's compute this integral now. Integral of dou f by dou x is integral of y squared by x squared with respect to x, which is going to be minus y squared by x plus a function of y. Now what we'll do is, we are given from here, from above, dou f by dou x, dou y is equal to q, which is 2y x squared, right? So differentiate star with respect to so q was minus 2, right? So minus 2y by x. So minus 2y by x. So differentiate star with respect to y will give me dou f by dou y equals to minus 2y by x plus hy of y, which will give me this. When I equate it with q, it gives me hy equals to hy of y equals to 0, which gives me h of y equals to a constant, right? Because the derivative of that with respect to y is 0, and it's purely a function of y. So h of y is a constant. We can take it 0 as well, but let's take it constant c. So therefore, f of xy is going to be minus y squared by x plus a constant c. So therefore, integral of f dot dr is going to be, substitute minus y, so we have minus of minus 2 squared by 4 minus of 1 squared by 1. Yeah, because it's connecting. Okay, so that is going to be minus 2, so this is going to be minus 1, right? This will cancel out. Minus 1 minus of minus plus 1, which is going to be 0. So now this is an interesting problem. So let's see, we have f equals to minus y over x squared plus y squared, x over x squared plus y squared. So what do we need to show? If this is my p here, this is my q, we need to show dou p by dou y, and dou p by dou y is going to be, you can apply the quotient rule and you will see that it's going to be y square minus x square upon x square plus y square the whole square. Similarly, you can see that dou q by dou x is also y square minus x square upon x square plus y square the whole square. And so we get dou p by dou x, dou y equals to dou p by dou x. Check. Yep. Dou q by dou x. So you can check that. However, let's see part B. So it is still not independent of the path. And why is that? Let's take a circle, basically. So let's take the circle here. Now we'll see that, let's take point 1, 0 to 0, 1. To minus 0, 1. Now let's take the upper part. So let's take these two paths. So this be C1. So let me just color that properly. So this be C1 and this part be C2. So let's write down the parameterization. So C1 is going to be given by x equals to cos t, y equals to sine t. Same parameterization for circle, but only halfway, so 0 to pi. Whereas C2 can be given as C2 can be given as, say, x equals to cos t, again y equals to sine t, but t goes from where to where? So t goes from t equals to 2 pi, okay? So now let's compute the integral of C1 f dot dr. This is going to be 0 to what? So 0 to pi. Now what is f? So instead of x, I'm going to put instead of y, I'm going to put sine. So I get minus sine t upon sine square t plus cos square t. Sorry, cos square t plus sine square t. Writing in the proper order. Cos square t plus sine square t. And we have again cos t. We have cos square t plus sine square t. Now, what is dr here? So dr is going to be derivative of cos is minus sine t. Derivative of cosine is cos t dt. So we have dot with minus sine t cos t dt. And if you look at this, it's going to be 0 to pi. Sine square t plus cos squared is 1. On top, you'll get sine square t plus cos square t divided by cos square t plus sine square t. And that dt. And along this path, it doesn't hit 0. It doesn't become 0 ever, right? So there's going to be integral 0 to pi of dt, which is pi. Now let's look at integral along C2 f dot dr. So same, the parameterization remains the same, right? Because we have cos t sine t, cos t sine t. So the only thing which will be different here will be from 2 pi to pi 1 dt, which is going to be minus pi. So you can see that these two integrals are not equal. So we know that C1 f dot dr is not equal to C2 f dot dr, even though they're joining the same points. So therefore what do we get? Therefore, integral is not independent of the path. Now, does this give a contradiction? And the answer is no, right? Contradiction to what? Look at the theorem 6 again closely. So if you look at theorem here, theorem, if f is conservative, then it is independent of the path. But so here we do have dou p by dou y equals to dou q by dou x throughout the d. But still f was not conservative because the integral along those two different paths were not same. And the reason for the failure was this region is not simply connected. So why this happened? D equals to R2 minus 0, 0 is not simply connected. So hence we got, therefore f is not conservative. On D. Okay, so that's the idea. All right, so thank you very much for your attention.